So we are at the final lecture in environmental plant physiology. It is the end of the semester, 22nd of April, Wednesday. Final exams start next week. This lecture is on nitrogen and nitrogen uptake, transformation, and metabolism. This is a topic that is covered in all plant physiology textbooks. Here's the plant physiology textbook, and if we open this up, chapter 5, assimilation of inorganic nutrients, and a big part of this chapter is nitrogen. So this is a similar topic, but it's a key part of plant physiology. That chapter we just looked at is assimilation of inorganic nutrients. So let's take a look at that. It doesn't say just nitrogen. How many essential nutrients are there in plants?
13, something like that.
It's in the teens. For years and years and years, we used to say it's 16 essential elements. Let's just review those. This is a review because you probably got this in 2 or 3 previous classes. The list of essential elements. The first 3 are carbon, hydrogen, and oxygen. Okay, the plant gets those from the air, so we'll take those out. We'll call that class number 1 from the air. Then if we put 2, the next 3 most important things are N and P and K. Those are the 3 elements we regularly add as fertilizers to help plants grow faster, and they're by far the biggest concentration in plants. Now, if we were to draw this to scale with the amount that plants have, oof, I couldn't even make this N big enough. If we were to draw this to scale, this would look like N and P and K. The N would be enormous. Hard to over-exaggerate it. There is more N in the plants than the sum of all of the other elements. And its metabolism is complex. That's why I'm focused on nitrogen for this lecture. Now, if we go to 3, now we're getting down into the still important but less critical, calcium, magnesium, and sulfur. These are typically inadequate in soils. We're much less common to fertilize them with them. They're still macronutrients. They're in percentages in the plants. Then we do 4, and I would put in a category all by itself, iron. This is the biggest micronutrient, and we usually draw a line here and say these are macros, these are micros. The concentrations get less and less. Doesn't mean they're less important, but iron has so much interesting chemistry. I've got a whole lecture just on iron, just by itself. And in fact, in human physiology, this is huge. We think iron availability controls diseases. There's a lot going on with iron. Now we get to micronutrients that are cations, Mn, Zn, Cu. Divalent cations. And then we can keep going. Other micronutrients, molybdenum is in here, really small. To make sure I'm not missing 1, 2, 3, 4, 5. Chloride is essential. And then the most recent addition to this, and it's what allows us to say our list of essential elements is now 17 elements, not 16. When I say new, it's new within the last 20 years. Nickel, Ni. 7, does that come out to 17? 9, 6 is 15, 16, I'm just thinking, am I missing anything? Ah, thank you, boron. And that's down here, B, boron. We could put 7, and there's a whole bunch of things in here that are beneficial but not essential. And chief among those is silica, really beneficial but not essential. And I won't go into all the other things. Even arsenic in trace amounts has some beneficial effects in plants. So now let's see if we got it. 1, 2, 3, 4, plus 3, plus 1 is 8, and 9 is 17. So there's our list of elements in plants. And in fact, if you get interested in this, in fall semester, I teach a class in plant nutrition, and this is the textbook for that class. A big encyclopedic book, and the fact that this is so thick tells you something about how much there is to know about plant nutrition. Trying to optimize all this stuff. N dominates everything. And here's why. Not only is it huge in this list, but let's look at the forms of elements. Calcium, 2+. Magnesium, 2+. Sulfur comes as SO4, 2-. Potassium, 1+. PO4 comes as PO4, which is typically 2-. How does N come? Ah, it is the only element that comes both ways. N can come as NH4 plus or NO3 minus. Now you start to get a handle on why this is so complex, because there's 2 forms. Here's a principle of chemistry that directly applies to plant physiology. It's charge balance. In a solution, there has to be equal numbers of cations and anions. And what that means is, if a plant gets more nitrate, the nitrate inhibits all of the anions in this table, because anions inhibit anions. And conversely, if a plant gets ammonium, it inhibits the other cations. So it's magnets, same principle of magnets. Like charges repel. And conversely, 1 over this, opposite, charges, I'll abbreviate, charges attract. So if you want to get more calcium into plants, this is a big deal. We're always trying to get calcium into plants. Back off on the ammonium, give them more nitrate. It'll draw in more calcium. That simple change has a much bigger effect on calcium than adding more calcium to the soil. That's how powerful this is. And just this simple principle tells you something about why you want to choose the form of fertilizer that's significant. That's a good introduction to this. Let me give another introduction. Back up. Here's the whole schedule, all the lectures. Here we are. Stress physiology, I'm out of order, but nitrogen is right here. The final is next Monday. I see that I have on here 11:30 to 1:20, but I have told people by email, same time as class time, 1 o'clock. So we're going to stick to that, and I'm going to change it right here, 1, and 1 p.m. Watch for the emails about this for starting at 1 p.m. I've initially said it's open book, you can have 4 hours. now the final is getting really long, and I'm thinking 4 hours is way too much. I'm thinking of making the final shorter and the time shorter, but it'll definitely start at 1 p.m. on Monday. It's probably going to be 3 hours long, not 4, just so it's going to be to your benefit. 9 cardinal parameters, we've looked at this before. Look at this, we clump everything as nutrients in here. Yeah, but if we did this, we could have nitrogen and a lot of things go into nutrients in terms of optimizing plant growth. And we're just going to talk about nitrogen today. This gets in to the nitrogen cycle right here. We talked about the Kelvin cycle, we talked about the Krebs cycle. These are people's names, of course. Now we get into the nitrogen cycle. But think of the importance. Well, we already got the importance right here. It's just, there's more N in plants than the sum of everything else put together. Proteins are, on average, proteins are 16% nitrogen by weight. That's an enormous amount of N. And in fact, how do we measure protein in plant tissue? We're doing that all the time. I'm going to put this way over here. If proteins are the average is 16% nitrogen. That's huge. When we measure protein in plants, we usually measure the nitrogen and we multiply by 6.25 to get percent protein. You see this number a lot. It's an average number to get proteins. Where does 6.25 come from? It's 1 over 16%. So this tells you something about, nitrogen's pretty much easier to measure than protein. So we measure the N and we calculate the protein in plant tissue. Nucleic acids are full of N. At 50% of the proteins in a leaf are rubisco. And rubisco, of course, is fixing all that CO2. Rubisco's loaded with N. One of the first things that suffers if N becomes limiting, you don't have as much rubisco, photosynthesis starts to go downhill. So it's critical. Abundance, where's all the N in the planet? Mostly in the air. 80% in the air. Now, it's worth it to have a sense of the nitrogen cycle. When we talk about abundance and transformations, the nitrogen cycle is in about 10 to the 6th biology books. It's probably in high school biology books. And people look at it, and when I look at those things, I think, really? This diagram is way overcomplicated. You can simplify the diagram to something you can remember. So now we're going to do nitrogen cycle. I'm going to erase air to give myself a little bit more room. 80% in here. There's the planet Earth. I'm going to put a little, and right in the middle of our diagram is a plant. And all good diagrams of everything in the universe should have a plant in the middle, and then everything flows around that. We already said 80% in air, so N2, it's always N2 gas, is up here in the middle, and there's 2 forms in the soil. I told you this was going to be simple. It's simple. Once you see it, you remember. NH4 plus and NO3 minus. There's the three components of the nitrogen cycle, and I'm going to put a circle around these. All right? How about arrows between these? There's arrows between all of these. How does the N get from the air to the soil? Is there an arrow here? No, there is not. Is there an arrow here? You bet there is. Nitrogen fixing plants, legumes. Huge. Before we had a way to chemically make N, this is how we got all of the N. That arrow going right to the plants. They take it, and what do they make from it? They make proteins, but those proteins degrade and go to ammonium. So N-fixing plants go to ammonium. This is only legumes. All the other plants sit there and they consume the N. They're not helping with anything because they're just consuming it. But N-fixing plants. Now, is there any other way the N gets from the air to the soil? Yep. Free living bacteria in the soil that are fixing N for their own needs. So now we got an arrow to these guys, microorganisms that are fixing it, and they in turn make ammonium. So far this is a pretty interesting, or a pretty simple diagram. You can remember we could put free living microorganisms there. Until we discovered a way to chemically fix N, these two amounts of N were about equal. About half the N in the planet was fixed by legumes, and a half was fixed this, and it went to ammonium. So here's nitrate sitting over there, all by itself with no arrows to it. How do we get N? These are connected. This has a famous name when it's mediated by microorganisms. This is a highly reduced compound, so it's high energy. And then it gets oxidized to nitrate, lower energy. So this is energetically downhill microorganisms. This arrow has a very famous name, nitrification. So, boom, this is continuously happening to NH4 over here to nitrate. So if this was the end of the cycle, we would have a tremendous amount of nitrate in the world because there's no arrows coming out of this. But what happens to nitrate? We have another arrow back up to here. And this is denitrification. Again, microbially mediated, but nitrogen's going back to N2 in the air. This is fine here. These are both used by plants. So now if we did just, let's put this maybe in brown. Both of these are taken up by plants. So they fix them, and now this could be any kinds of plants, but they're both going into plants. So you can start to see you're getting a little more complex here. Denitrification is not a great thing because we lose the nitrate. We lose a soluble form that's valuable for all of plant biology, all of microbial. But if it goes back to N2, dang it, we lost it. We've got to get it back again. And it's hard work getting it back again. These two arrows here are energetically very uphill. This is an enormous amount of work to get this way. And after that, boom, it flows downhill back to this. There's one more arrow in this. Ammonium, so far it only goes this way, but ammonium can go to NH3, which is a gas. And that NH3 then can go to N2. This is again downhill energy-wise. These two arrows we try to minimize. This happens with pH. And as long as a pH is below about 7, it stays as ammonium. But if the pH gets high, it starts to go to NH3 and then finally to N2, gas in the air. This is a good time to talk about the effect of pH on this, because let's put this right here. This is pH, and this is form of N. And here's 0, 100%. And here is pH. If I see this, 9.15, right in the middle. That's a high pH. Here's pH. And now we're going to do, oops, going the other way, 10.15, 11.15. You'll see why I've chosen these in a second. 8.15, 7.15. All right. So roughly this scale goes from pH 7 to 11. So neutral to very alkaline. If we get relatively more acid, 100%, this is NH4 right here, is in the ion form. It's water soluble, it's steady, but as soon as the pH starts to go up, this changes and it looks like this, and the NH4 goes to 0. And then the other line on this, let's put this one in red. What's it going to? NH3. NH3 is 0 here, and it's the exact inverse of this. So as the pH goes up, it switches forms. And really we could write NH4 plus OH goes to NH3 plus H2O. So this is back and forth depending on pH. Here's the reason this diagram is so important, and really for the whole planet. These are nonlinear. This point right here, where they are at 50%. There's a special special name in chemistry for this point, and if you had enough chemistry classes, you would have heard of this. You ever heard of this point?
I'm sure.
pKa. It's pH. It is the point at which there's a 50-50 mix of two compounds. You can look up in charts of everything in this. Phosphorus has pKa's because it's HPO4 and H2PO4. There's lots of compounds that gain charge and lose charge based on pH. And for all of those compounds, of which there are many, they all have a pKa, and you can look it up. And then once you know the pKa, you can make this chart for them. This is particularly important in all of biology for nitrogen, because this is ammonia. And this over here in green is ammonium. Ammonium is the ion form, water soluble. This is a gas. And what do we clean windows with? Ammonia window cleaner. This is really reactive and really toxic to plants. And this form is much safer. And if the pH creeps up, you lose it as a gas. You permanently lose it. This is one of the things we're working on with NASA, how to recycle nitrogen. Keep it in these forms. Don't lose it. Don't let it go up here. In fact, the whole planet's working on this. We just got to keep it sufficiently acid. Now, at 1 pH unit, this is 10%. At 2 pH units, this is 1%. So it doesn't go to 0 at 7.5, it just goes to 1% of the total. 1% is NH3. What's our pH of our soils in Utah, typical pH? So we're losing nitrogen a little bit, continuously losing it as a gas. Of course, we're trying to get it into the plants fast so we don't lose it. But so this is the nitrogen cycle and the transformations between plants. There's one big thing on here. Draw this in black. In World War I, Germany was making bombs with nitrogen. And they had two scientists that, this was such a challenging thing, two scientists that are working on this. It was enormous for agriculture. It was also enormous for bombs. And they figured out with catalysts and high temperatures and pressures, they figured out how to get nitrogen from the air into ammonia. So this black line in this is, everything is natural until this point, but they figured out how to get nitrogen from the air and fix it. This is way uphill energetically, but suddenly we had a lot of ammonium. And I like to make this story memorable by drawing a little factory right here with a door and a chimney and smoke coming out of it like that. This process has a very famous name that everybody memorizes for various classes. Here's the two scientists right here. And one of them figured out how to do it in the lab, and the other one figured out how to scale it up big. So they had to work together. One guy said, okay, I can do it. And the other guy said, let me scale it up. And they worked together. It's not Mickey Mouse. But bonus points, what's the name of these two scientists? Fritz Haber and Karl Bosch. They both got Nobel Prizes. This is considered the greatest feat of chemistry the world has ever known. That's how important it is. And it was incredible. All of a sudden, our nitrogen diagram changed life on the planet forever because we got more ammonium. And of course, at the time, we could make more bombs, but more importantly, we could feed agriculture. And it dramatically improved yields because we had ammonia. Here's the downside. It takes enormous amounts of fossil fuels to do this. I've forgotten the number, but a huge fraction of the world's fossil fuels are going into this plant right here to fix N. We're working hard on biological ways so we don't need this anymore because it's a problem. Not only does it take a lot of fossil fuels, but now we have reactive nitrogen all over the planet, in rivers. There's whole papers written on the problems of all this reactive nitrogen because we get a big pool of ammonia feeding this thing. So there's the nitrogen cycle, simplified, and the importance of all the transformations. Now let's do uptake. This is another very simple thing, and we're going to show uptake. We're going to take a little section of plant root right there, and we're going to blow it up. And here's a giant plant root. Here's the soil up here. Because of charge balance, when a plant takes up ammonium, hydrogen comes out. So it makes the soil more acid, makes the rhizosphere more acid, fundamentally. When a plant takes up, let's put nitrate over here. Nitrate, the opposite happens. Hydroxide comes out. Technically, it's compounds leading to hydroxide, but so when we give plants nitrate, makes the pH go up. We give them ammonia, makes the pH go down. Think about this for plant nutrition in alkaline soils. We get 7.8. We got all kinds of things. The phosphorus in our soil, plants can't get it. The pH is too high. A whole bunch of things are tied up. What form of nitrogen should we be feeding plants in Utah? Because we can acidify the soil. And if you go to the store, you rarely see nitrate forms in the stores because it makes the soil worse, makes it even more alkaline. Ammonium sulfate, sometimes you might see ammonium nitrate, lots of fertilizers with high ammonium. Now this hydrogen sometimes it only acidifies the rhizosphere right next to the plant, but that's all it takes. And it's so powerful, studies have shown if you give plants nitrate, you can drop this by 2 pH units. You can make this go from 7.8 to 5.8, right in the rhizosphere. Really hard to change bulk soil pH, but we can change the rhizosphere. This is huge. If you go east of the Mississippi River, all you see is nitrate fertilizers because there it rains a lot, their soils are too acid, they're trying to get the pH up. So they're feeding nitrate to plants and to get the pH up. This comes from that principle over there, charge balance. We've got to maintain charge balance. There's plenty of studies showing this. We study it by putting roots on litmus paper. And you can see the plants changing the pH of the litmus paper depending on the form of nitrate and ammonium. If I was better organized, I would have had to do that. And we'd have some litmus paper here with some little plants, and you could see it changing the litmus paper. But you can do that yourself. It's a pretty easy test. Okay, this is uptake. How about transformation and assimilation into usable forms? And this is the final square on here. I'm out of room right here. I'm going to leave this, and then we're going to go all the way over here. And we're going to put this next topic right here. We can leave the proteins. There we go. We got enough room. Here's our plant. One root down here. We have NH4 over here. We have NO3 over here. Now we go to the top of the plant. Green. This is a real simple plant, right? We have a leaf. Here we go. What happens when a plant takes up ammonia? Well, first of all, what's the end goal up here? Proteins. We want to get this assimilated into proteins. So proteins in chemistry are NH2 amino groups, and amino acids are simple compounds with a lot of NH2s on them. Well, NH4 is a lot closer to this than nitrate. Remember, this is an oxidized form. It's low energy. So if we were doing some kind of energy thing, wow, the nitrate has to get reduced to NH4, and then this gets assimilated into amino acids, and then the amino acids become proteins. This step right here is called assimilation. So, takes a lot of energy to make these proteins. The ATPs are flowing into this thing. To get it, you would think we could grow better plants if we feed them with ammonia, NH4, than feed them with nitrate, just from the energetics of this. And that is rock solid analysis, but they don't. We've done many studies and we don't see a difference. And it's like, why not? Here's the difference. First of all, ammonium is taken up about at least 100 times faster than nitrate. If we did this, we'd have a huge arrows. I'm going to put 100 to 1,000x faster uptake. This uptake is really rapid compared to nitrate. When ammonium gets in the plant, what's the pH of the cytoplasm of a plant, of the biological? It's controlled tightly. We're going to have our big diagram here. Cytoplasm. This is controlled at about 7.15. That's to 3 digits, but I mean plus or minus a few hundredths of a pH unit. This is very slightly alkaline. What do we know about what happens in here? Yikes. So now NH4 comes in, and some of that goes to NH3. Not very much, but guess what? You just made window cleaner in your plant cells. That is not a good thing. This is toxic to plants. And if this is taken up super fast, we got to use it fast. So what happens is right here, it goes to R and H2. In the root, carbohydrates come down. I'm going to put CH2O. Carbohydrates come down. They're respired in the roots, in the mitochondria. Plenty of ATP. It gets made into amino acids, and then the RNH2 goes up here to the leaf. So it's a pretty simple story, but we've got to have steady supply of carbohydrates. We've got to have right temperatures so that this all happens, so we minimize the ammonia in here. And this gets tricky. You feed plants high levels of ammonia, and the whole thing can't stay in balance. We talk about fertilizer burn of winter crops in greenhouses. It's because it's cool and low light. And if it's low light, there's not enough carbohydrate, and this can't be assimilated fast enough, and it leads to some toxicity. So this is a tricky form of N, but it works fine if everything's optimally good temperatures, good carbon. There's ATP getting made in the roots. Everything's good. Nitrate is considered the safe form of N. And because it's safe, we're going to show that in a blue color. Nitrate can go in. Now, first of all, the uptake is fast of both of these, but it's more regulated than ammonium rather. When nitrate gets here, It can also be assimilated, more energy though, because more steps into NH2, and then that goes to the top. But because nitrate is safe, there's not this issue of making ammonia in the plants. It can be stored in the vacuole. E, nitrate. And plants can store a lot of nitrate in vacuoles. They take it up, we've got it, let's put it in the bank for future use. So this is completely safe. And it can be stored in vacuoles up here too. Everywhere in the plant we can and plants do store nitrate. And they try to get ahead of the game. They try to get extra and put it in the bank because it can be easily taken back out of the vacuole at any time. So there's two options: assimilation, storage. But here's the amazing thing: nitrate is really mobile in plants. Ammonium is not very mobile at all. Nitrate can go up to the top, and it's nitrate up here, translocated to the top. And you say, okay, and up here it can be stored. It can, and it is stored. It can be assimilated, but here's the amazing thing. Remember the light reactions of photosynthesis make, let's see if we can draw this quickly. Light coming in, photons, our smiling photons are coming in. The first step of this is to make ATP. This is called photophosphorylation, because photo from light. There's no mitochondria in this. This happens in the chloroplast. ATP are made directly. Now, most of those ATP are used to fix CO2, because that's the key thing. But there's still a lot of ATP up there. Guess what? We can use those ATP to reduce nitrate to make amino acids. It's called photoassimilation. Photophosphorylation, that's a long word, photophosphorylation, and then photoassimilation up here. This is an enormous shortcut for plant metabolism, because you don't need to make carbohydrates, you don't need to ship the carbohydrates around, you don't need to put the carbohydrates in the Krebs cycle. You just directly use the ATP to fix N. It's incredible. So that is why when we do studies, you would think the ammonium would always grow better plants than nitrate, but nitrate has this shortcut right here. And on balance, both of them work equally well to grow plants, provided you can get enough N in the plants and everything like that. But this ATP shortcut is huge. I guess we could put on here one other little thing, and that would be, if we draw it up here, seeds. Depending on what kind of plant it is, seeds. And of course, many seeds are loaded with protein, but all these amino acids and go into the seeds. And that's the ultimate thing, high protein food crops. But it happens either here or here. How many plants can do this shortcut? Can all plants do it equally well? It turns out, no. This is a chart, which I'll send you as a handout. I need to simplify this chart. It's right out of a journal article. But it's how much of the nitrate is assimilated in the chloroplast and how much is assimilated in the roots. And I can just tell you the answer to this. It varies. Some plants do most of the work in the leaves, some do it mostly in the roots. You would think all plants would do it in the leaves, but that's not what we find. Clovers, cocklebur is not a crop plant, but clover and cockleburs assimilate most of the nitrate in their leaves. They do very little in the roots. Peas, radishes assimilate most of the N in the roots. So some species take this shortcut a lot better than others. And it's a potential for plant breeding to breed in the shortcut to more plants. It's an amazing thing. I think that's, now one more thing. Almost everything. Why do we even have this? Why don't we just grow more legumes? And in fact, if they both do this, and in fact, not only alfalfa is a great legume for fixing N, and we have a lot of alfalfa in Utah, a lot of it in Cache Valley. Guess what? We take fertilizer from Haber-Bosch and put it on alfalfa. Wait a minute, this fixes its own N. Why are we doing that? It's economics. It is cheaper to pump out of the ground fossil fuels, fix N with Haber-Bosch processes, ship them across the country and fertilize alfalfa than it is to have the alfalfa fix it by itself. And if that seems bizarre, here's the problem. This is so energy intensive, when the legumes have to fix their own N, the yield goes down. They're taking a lot of ATP to fix N. So it's sort of sad that the economics favor fertilizing legumes when they can do it themselves, but it makes the yield go up because they didn't have to make their own N. And this is a little diagram that I have assembled to show this whole thing on one page. Biological N and industrial over here. Legumes and bacteria, and here's Haber-Bosch, Nobel Prize 1980, 1931. There's great books written about this. One of my favorites is called The Alchemy of Air, and it's about how they made the discovery. They were both, like many scientists, they were half crazy. Let's just put it that way. And they both had really interesting lives, and they were both in and out of politics with Nazi Germany. I mean, because they were being forced to do this because of bombs. It's really interesting. So here, both of them start with N2, and this uses 8 electrons and a lot of sunlight, and this uses fossil fuel, or methane, and they both make NH3, and then that goes to NH4. And I'll send you this as a handout. Fossil fuels, over here, nitrogenase enzyme. This is a huge enzyme. When you run the numbers, the energy per this, 500 kilojoules of ATP per mole of ammonium fixed. Fossil fuels, you run the numbers, 500 kilojoules of fossil fuel energy per mole of ammonium. These two numbers are the same. That is a huge number, and they're equal. And that's why we use fossil fuel N. And it's sort of a shortcut, as long as you got plenty of fossil fuels to run this thing. All right, I'm going to stop there. This is the story. And if you like plant nutrition, you should take a plant nutrition class. Everyone should have the final exam from last year, so study that. I would encourage everyone to make a page of notes. This is going to be a timed test. You're not going to be able to go back and review stuff. You're going to have stuff on the tips of your fingers to be able to finish the test. Even though it's open book, you're going to have to be very organized to know where stuff is, to do well on it. We are standing by to help you with that last year's exam. If stuff is unclear, anything else that's unclear, watch your emails. Good luck. I hope every single one of you does tremendously on the final exam. I'll see you again sometime soon.